Lecture 8-3, Concentration of Solutions. Concentration units specify the amount of a solute dissolved in a given amount of solvent. The amount of solute is often expressed in units of mass, such as in percent mass per volume, and parts per million, ppm. The amount of solute can also be expressed in moles, such as in molarity and molality. The amount of solvent can be volume, as in the case with molarity, percent mass per volume, and percent volume per volume. But it can also be expressed as mass, as in the case with molarity, percent by mass, and parts per million, ppm. The term concentrated refers to a solution which has a relatively large amount of solute in the solution, whereas the term dilute refers to a solution having relatively small amounts of solute. Molar concentration, or molarity, is the number of moles of solute per liter of solution. It is represented by a capital M. Mathematically, molarity, M, equals moles in divided by volume, V, in liters. A chemical formula enclosed in square brackets is the representation for the molarity of a solution with that particular chemical species as the solute. For example, HNO3 in square brackets indicates that the molarity of nitric acid is desired in moles HNO3 divided by liters of solution. Molarity calculations come in three varieties. First, the molarity can be calculated from a given amount of solute and the total volume of the solution. Second, the volume of the solution can be calculated from a given molarity of a solution and the amount of solute in the solution. Finally, the amount of solute needed to make a specified concentration of a solution in a certain volume can be calculated. The first will be demonstrated on this slide, and the other two on subsequent slides. In this problem, 45 grams of potassium iodide will be dissolved in enough water to make a solution with a volume of 500 milliliters. Since molarity is moles divided by volume in liters, the mass will have to be converted to moles, and the volume will have to be converted to liters. Then the molarity can be calculated. The moles of potassium iodide equal 45.00 grams Ki divided by 166.00 grams Ki per mole Ki, giving 0.27108 moles Ki. The volume of the solution in liters is 500.0 milliliters divided by 1,000 milliliters per liter, giving 0.5000 liters. Thus, the molarity of the potassium iodide solution is 0.27108 moles Ki divided by 0.5000 liters of solution, given a concentration of potassium iodide as Ki in square brackets equals 0.5422 capital M or moles per liter. In this second problem, the concentration of sodium hydroxide solution is given as 3.50 molar or 3.50 moles NaOH per liter of solution. The volume of the solution in milliliters is desired given that the solution is made with 75.00 grams of solid sodium hydroxide. Since M equals N divided by V, to find the volume, rearrangement yields volume V equals N divided by M. Thus, the mass of the sodium hydroxide will have to be converted to moles, then divided by molarity. The volume will be in liters and will be needed to convert to milliliters. The molar mass of sodium hydroxide, NaOH, is 40.00 grams per mole. The moles of NaOH equals 75.00 grams. NaOH divided by 40.00 grams per mole, which is 1.875 moles of sodium hydroxide. The 1.875 moles sodium hydroxide is divided by 3.50 moles sodium hydroxide per liter of solution. Which gives 0.536 liters of solution. Multiplying this by 1,000 milliliters per liter gives us the needed 536 milliliters. The process of making a solution with a known concentration in a known volume first involves calculating the mass of the solute desired to make the solution. This amount of solute is usually added to precise measuring instrument such as a volumetric flask. About half of the desired solvent is added to dissolve the solute. The solution is then mixed until the solute is completely dissolved. Once dissolved, more solvent is added until the bottom of the meniscus reaches the calibration line for the glassware. The calculation of the mass first requires the calculation of the moles of solute using the molarity M and the volume V in liters. Mathematically, the number of moles equals the molarity multiplied by the volume, or N equals M times V. To calculate the mass of potassium iodide needed to make 500 milliliters of a 2.80 molar solution, the volume must be converted to liters and then multiplied by the concentration to get the number of moles of Ki. 500 milliliters is divided by 1,000 milliliters per liter, giving 0.500 liters. This is then multiplied by 2.80 moles of Ki per liter of solution, giving 1.40 moles potassium iodide. Moles are then converted to mass using the molar mass of potassium iodide, 166.00 grams Ki per mole Ki. And this equals 232 grams Ki. Dilution is the process whereby a concentrated solution has solvent added to it, reducing the concentration of the solution. Typically, a stock solution of high concentration is diluted with solvent to give a solution with a much lower concentration. Such is the case when we make dilute acid solutions for use in the lab. For example, if a 0.1 molar solution of hydrochloric acid is desired, a small amount of concentrated HCl, about 12 molar, is diluted with deionized water to make the desired concentration. Given the concentration of the stock solution and the molarity and volume of the dilute solution, the amount of stock solution can be calculated using the formula M sub C times V sub C equals M sub D times V sub D, where C denotes the concentration of the concentrated solution and D denotes the dilute solution. Note that the number of moles of solute does not change in the dilution process, only the volume changes. 250 milliliters of a 0.10 m copper 2 chloride solution is needed. There's a stock solution of 2.0 m available. Describe how this dilute solution is prepared. First, calculate the amount of the stock solution needed using M sub C times V sub C equals M sub D times V sub D. Algebraic rearrangement yields V sub C equals M sub D times V sub D divided by M sub C. Thus, V sub C equals 0.10 molar times 250 milliliters divided by 2.0 molar, which equals 12.5 milliliters. To make the solution, put 12.5 milliliters of the 2.0 molar stock solution of copper 2 chloride into a 250 milliliter volumetric flask. Then add enough water to reach the calibration mark. Stopper the flask and mix. The resulting solution will be 0.10 molar. A solution of sodium nitrate is made by mixing 32.56 grams of NaNO3 into a total volume of 925 milliliters. Calculate the molarity of the solution. This is done by converting the mass of sodium nitrate into moles sodium nitrate and by converting volume to liters. Then take the moles NaNO3 and divide by the volume in liters. The molar mass of sodium nitrate is 85.00 grams NaNO3 per mole NaO3. Thus, the moles of sodium nitrate are 32.56 grams NaNO3 divided by 85.00 grams NaO3 per mole of NaNO3, which is 0.3831 moles NaNO3. The volume in liters is 925 milliliters divided by 1,000 milliliters per liter, giving 0.925 liters. The molarity is then 0.3831 moles NaNO3 divided by 0.925 liters, which is 0.414 molar. In this problem, the mass of barium chloride needs to be calculated to make a 0.250 molar solution, which has a volume of 375 milliliters. Volume is converted to liters by dividing by 1,000 milliliters per liter, yielding 0.375 liters. The moles of barium chloride are calculated using N equals M times V, which gives 0.250 times 0.375, or 0.0938 moles of barium chloride. Multiplying this by 208.23 grams BaCl2 per mole BaCl2 gives a mass of 19.5 grams. Soluble ionic compounds, as specified by the solubility rules, dissociate completely in aqueous solutions. The concentration of the various ions can be determined from the molar ratios in the chemical formula. For example, sodium chloride dissociates into 1 sodium ion and 1 chloride ion. This means that a 1 molar solution of sodium chloride produces 1 molar sodium cations and 1 molar chloride anions in the solution for a total of 2 molar ions. Sodium sulfate dissociates into 2 sodium ions and 1 sulfate ion. Thus, a 0.25 molar solution of sodium sulfate produces 0.50 molar sodium cations and 0.25 molar sulfate anions, with a total of 0.75 molar ions in solution. Finally, aluminum chloride dissociates into 1 aluminum ion and 3 chloride ions. Thus, a 0.20 molar solution of aluminum chloride dissociates into 0.20 molar aluminum cations and 0.60 molar chloride anions, with a total of 0.80 molar ions. A 0.125 molar solution of magnesium chloride dissociates into 0.125 molar magnesium cations and 0.250 molar chloride anions. 0.25 molar barium hydroxide dissociates into 0.425 molar barium cations and 0.850 molar hydroxide anions, with a total of 1.275 molar ions. 0.168 molar sulfuric acid can dissociate into 0.336 molar hydrogen cations and 0.168 molar sulfate anions, giving a total concentration of 0.504 molar ions. 0.525 molar ammonium chloride dissociates into 0.525 molar ammonium cations and 0.525 molar chloride anions, for a total of 1.050 molar ions. Aqueous reactions and chemical analysis. The following slides will describe 2 useful types of quantitative analysis: volumetric analysis and gravimetric analysis. Volumetric analysis, often synonymous with titration, is a set of methods where a solution of accurately known concentration is gradually added to a solution of unknown concentration until the chemical reaction is complete. The endpoint of the reaction is often recognized by a change of color of an indicator substance. Gravimetric analysis is a set of methods used to quantitatively determine the amount of a particular chemical species based upon the mass of a solid precipitate. Acid-base titrations involve neutralization reactions. The unknown solution is accurately measured into glassware, usually an Erlenmeyer flask. This solution is often diluted with deionized water, and an indicator is added such that the endpoint of the reaction can be seen. An indicator is a substance that is added in a small amount and that changes color at or near the endpoint of the reaction. The endpoint of the reaction, also known as the equivalence point, occurs when the acid and base are in stoichiometrically equivalent amounts such that neutralization has occurred. In this case, neither the acid nor the base are in excess. A standard solution, which has a known concentration, is then slowly added until the equivalence point is reached as shown by the indicator. The volume of the known solution can then be determined. By knowing the volume of the unknown solution and the concentration and volume of the known solution, the concentration of the unknown can be calculated. The formula of the acid, M sub A, times the volume of the acid, V sub A, divided by the stoichiometric coefficient of the acid in the balanced neutralization reaction equals the molarity of the base, M sub B, times the volume of the base, V sub B, divided by the stoichiometric coefficient of the base in the balanced chemical reaction. 15 milliliters of an unknown monoprotic acid solution is placed in an Erlenmeyer flask with an indicator. It was then titrated with 0.12 molar standardized solution of sodium hydroxide. The volume of the base used in the titration was 35 milliliters. What is the concentration of the acid? Because this is a reaction of a monoprotic acid with sodium hydroxide, the stoichiometric coefficients for the acid and base are 1. The formula to solve is molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Solving for M sub A, the concentration of the acid, the formula is M sub B times V sub B divided by V sub A. Thus, the concentration of the acid, M sub A, is 12 molar times 35 milliliters divided by 15 milliliters, which is 0.28 molar. Note that the volumes do not have to be changed to liters since both volumes are given in the same units, milliliters. Your turn. Calculate the molarity of 25 milliliters of a monoprotic acid if it took 45.5 milliliters of 0.250 molar potassium hydroxide to neutralize the acid. Again, solving for M sub A, the concentration of the acid, the formula is M sub B times V sub B divided by V sub A. Thus, the concentration of the acid is 0.250 molar times 45.50 milliliters divided by 25.0 milliliters, giving a concentration of 0.455 molar of the monoprotic acid. What volume of 0.5 molar hydrochloric acid is needed to neutralize 75 mL of 0.15 molar barium hydroxide? The balanced chemical reaction is 2 moles HCl plus 1 mole barium hydroxide produces 1 mole barium chloride plus 2 moles of water. The formula to solve is molarity of the acid times the volume of the acid divided by 2 moles of acid equals molarity of the base times the volume of the base divided by 1 mole of base. Solving for the volume of the acid, V sub A, the equation is M sub B times V sub B times 2 divided by M sub A. Thus, V sub A equals 0.15 molar times 75.0 milliliters times 2 divided by 0.50 molar, which equals 45.0 milliliters. The typical steps of gravimetric analysis involve obtaining the mass of the unknown solid, dissolving the unknown solid in water, reacting the unknown with an excess amount of known substance to form a precipitate, filtering, drying, and weighing the precipitate, using the formula and mass of the precipitate to find the mass and the percent of the unknown ion in the original sample. A 0.825 gram sample of an unknown ionic compound containing chloride is dissolved in water and then treated with excess silver nitrate to form silver chloride as the precipitate. 1.725 grams of silver chloride is collected. What is the percent by mass of chlorine in the original sample? First, find the percent chlorine in silver chloride. The percent chlorine equals the molar mass of chloride, 35.45 grams per mole, divided by the molar mass of silver chloride, 143.32 grams per mole, times 100, which equals 24.73%. Multiplying 1.725 grams of silver chloride by 24.73% yields 0.427 grams of chlorine in the sample. 0.427 grams chlorine divided by 0.825 grams of the sample times 100 gives 51.7% chlorine in the original sample.